Hi, my name is John Paul Raj, and I'm on a mission to make the learning of math fun. So if you're new to this channel, please do consider subscribing. This is part 3 of transformations of functions. If you haven't already seen any of the earlier videos, I'm going to link them in the description box below. Please go ahead and take a look at them. Let's start. In order to make a proper study of dilations of functions, it's important to study the dilations from the x-axis and the dilations from the y-axis separately, all right? Dilations from the x-axis are of the form y is equal to a times f of x, okay? What does that mean? If f of x is any parent function, let's consider the quadratic function as a parent function, and a is any number, any numeric value, a factor. It could be greater than 1, it can also be less than 1, okay? So it can be something like 1/3. What's happening is that this a gets multiplied to every y value, okay? So we're talking about dilation from the x-axis, a factor of a is equal to 2, so you're multiplying every y value of the parent function by a factor, like 2. But what does that look like on the graph? Let's find out, all right? So let's add a graph page. And our parent function we're considering is the quadratic function. So y equals x squared. Let's just move this label somewhere there. And I'm going to enter the transformed function like a times f1. All right. And you notice that f1, the moment I've typed f1, it's becoming bold because the calculator recognizes that f1 of x is that, by the way, it's already asked for a slider because a was a non-numeric factor that we've entered. All right. And whenever there's non-numeric, it's going to create a slider, all right? So that's a times f1 of x. f1 was x squared, and at the moment, it looks like the blue graph has gone well. It's actually under that graph because a is equal to 1. Look at the slider value, a equals 1. So when a equals 1, it's like saying 1 times x squared, so it's the same graph. Well, it's right on top, okay? The red graph is right on top of the blue graph, which is why we can't see it right now. Let's just go and change the settings of the slider. A is fine, value is fine, minimum, maximum is fine. Step size, let's make it 0.2, all right? And then the minimized slide is what I like, these buttons, okay? So I'm just going to try and move it somewhere here, all right? That's good. This label, you're going to move it here. And as you can see, A is 1, all right? And that's why it's right on top of each other, okay? It's coincident. Now, when we increase the value of a to, say, 1.2, that was the increment. Remember, the step size was 0.2, 1.2. What just happened? It was right on top of each other. It looks like the red graph is moving away from the blue graph, but moving towards the y-axis, okay? Towards the y-axis. A was 1, and now it's become 1.2. Greater than 1, moving towards the y-axis. Now, further greater than 1. Further greater than 1. So for values of a greater than 1, it looks like the red graph, the transformed graph. Remember, it's a dilation from the x-axis. It looks like the red graph is moving towards the y-axis. Okay, let's see further, all right? So as you go, can you see that? It's moving closer and closer and closer. It looks like it's moving closer and closer to the y-axis. This is a dilation from the x-axis. Those words are important. Dilation from the x-axis. And it looks like it's moving closer to the y-axis. Okay, let's watch more. There you go. Okay, that is true. It is true. It's moving closer and closer to the y-axis. Now let's compare some corresponding values. So let's just shift this graph here, and we'll make use of trace all. Okay, so that's a nice feature to compare corresponding points. So for x equals 0.6 on the blue graph, which is the parent function, the same 0.6 on the transform function, the values of y, can you see the corresponding values of y? They're different. And what do they differ by? They differ by that value of a. A is 3, so it's almost like saying that's 3 times. The y value is 3 times. And as we move along the trace function, can you see that? Look at these values here. For the same value of x, compare the values of y. The value of y, 2.25, is now 6.75. That is 3 times. So when you look at these points, these are the corresponding points, okay? At 1.5, at x equals 1.5, the parent value was 2.25, but now it's almost like it's jumped there, okay? So the same value has jumped up there. In other words, that point has stretched away from the x-axis. That's why we call a dilation from the x-axis, okay? Stretched away from the x-axis, but the stretching is along the y-axis. Notice the choice of words. Stretched from the x-axis, but that stretch is happening along the y-axis. Okay, that's why it's affecting only the y-coordinate and not the x-coordinate. Okay, let's move that trace again, and you can see further. Can you see that? Stretching for every value. Okay, 0.2. How much that stretching is. It's almost like stretching by a factor of 3, and therefore it looks like, it's moving closer to the y-axis. But that doesn't give a great idea. That's why we have to compare. Okay, it's a stretch from the x-axis, but that stretch is affecting the y values. So in a sense, it's a transformation of the range. Okay, now let's see what's going to happen when we change the value of a to less than 1. Okay, this was like greater than 1. We're seeing that the y values are getting stretched. The y values are getting stretched, and not only are they getting stretched, but the graph looks like it's moving closer towards the y-axis. Now let's do, like I said, let's observe what's going to happen when the value of a is less than 1. Okay, watch the graph carefully. So let's bring it back to 1 first. Okay, so at 1, it's going to be on top of each other, but keep an eye on both the coordinates here as well as on the graph. Okay, now a less than 1. All right, a less than 1. Watch what's going to happen. A less than 1. All right, a less than 1. Can you see what's happening? It looks like the graph, the transform graph, is moving away from the y-axis, but moving towards the x-axis, Now this moving towards the y-axis or moving away from the x-axis can be ambiguous. All right, it is true. It's true that it's moving, but what you need to really pay attention to is the y values. For corresponding values of x, when x is 1.8, the y value, all right, can you see that? The y value was 3.24, but that's actually 0.4 times that. Okay, that's what's happened. Okay, 1.3 is actually 0.4 times that. Okay, that's what's happened. So in one sense, what's happened is that the y value is getting shrunk. Okay, earlier it was getting stretched, but now the y value is getting shrunk. Okay, and it's getting shrunk again from the x-axis. Okay, those choice of words, from. The y values are getting shrunk, but from the x-axis. So actually it's affecting the y values, affecting the range, but it's a dilation from the x-axis. I want you to see this transformation. Okay, see that further. Okay, no, we want to reduce. Sorry, we want to reduce. And when it becomes 0, it's almost like saying 0 times x squared, and therefore that's a flat line there. So greater than 0, but less than 1, it looks like the graph is somewhere towards the x-axis. But remember, it's a shrink along the y-axis, But when it's greater than 1, okay, the graph looks like it's moving towards the y-axis, but it's a stretch along the y-axis, So let's make a note of this quickly, all right? What we are seeing is a dilation from the x-axis, okay? Dilation from the x-axis is a times f of x, okay? It's affecting the y values, as we said, okay? And what we observed in the graph was something like this. When a is greater than 1, we observed that the graph moves towards the y-axis. Towards the y-axis is the same thing as moving away from the x-axis, but you know what's happening also is that the y values are getting stretched, okay? Y values stretched. So that's like saying stretched along the y-axis, okay, which is why we also call it a transformation of the range, okay, stretched along the y-axis, but it is also sometimes referred to as stretch from the x-axis. Okay, so these are to be used synonymously, all right? Stretched along the y-axis is like saying stretched from the x-axis. It's like saying that the x term is invariant, okay? It's only the y term is getting multiplied by a factor of a, all right? Now, that is when a is greater than 1. When the value of a is less than 1, but still positive, okay? Still positive, a is less than 1, but still positive. We saw that the graph moves towards the x-axis. Towards the x-axis, okay, you saw that it was flattening, and when a becomes 0, it was, flat on the x-axis. So it was moving towards the x-axis, almost like saying moving away from the y-axis. But the y values, there was a shrink, okay, shrink in y values. And that's like saying that it's shrink along the y-axis, which is the same thing as shrink or compress. They are, compressing or shrinking, or a shrink from the x-axis. Okay, this is what I want you to be careful about. The along, this is just the language. These are semantics, but just be careful. Shrink along the y-axis, but it's a shrink from the x-axis, okay, because the x term is remaining invariant. It's just the y-axis are getting multiplied by a factor, okay, the factor less than 1, but still positive. It's a shrink in y values, whereas when a is greater than 1, it's a stretch in the y values. And therefore, let me go along here, a dilation from the x-axis is often referred to as a transformation of the range because it's affecting the y values. All right. Now, what's going to happen when the value of a is negative, a -2, -3? What's going to happen? Let's find out. Okay, so here we are on the graph again. This is a equals 3. Okay, we already saw this before. Let's make it negative. Okay, so we are reducing to 1 where, both the graphs are on top of each other. Let's just arrange this slightly differently now. So we can see what's going to happen. Okay, so now as it reduces, as the value of a is less than 1, okay, it's moving closer to the x-axis, and a equals 0 is a flat line because it's 0 times x squared, that's the x-axis. Now keep your eyes on these coordinates also, and also on this graph, okay, as I reduce a further below 0. Whoa, what just happened? -0.2, it's almost flipped, reflected, all right? Watch these coordinates, okay? Now, what's going to happen further? Okay, watch further, all right? That means it's moving closer and closer to the y-axis, but a reflected form of it, okay? So as we keep reducing, you can see that when it hits -1, it's a clear reflection. Look at these points. X is 1.8 for both the graphs. The parent function is blue. The transform function is the red graph. 3.24, -3.24. That's a clear reflection about the x-axis. So basically what's happening is that whenever you have a negative value for a, it's a reflection about the x-axis. But every other behavior that we saw, all right, so for further values, that means the magnitude of a, the absolute value of a, if that is greater than 1, the graph is going to go closer to the y-axis. Yes, it's a reflected graph, but it's going to go closer to the y-axis, which is a stretch along the y-axis, but from the x-axis. So let's make a note of this. We just saw that regardless of the sign of a, as long as the absolute value of a is greater than 1, the graph still moves towards the y-axis, all right? A is negative, that's a reflection, but it's still moving towards the y-axis. The y values are getting stretched. It's a stretch along the y-axis, which means it's a stretch from. Remember those words, okay? Semantics, but important semantics. Stretched along the y-axis, but stretched from the x-axis, okay? So as long as the absolute value of a is greater than 1, it's a stretch along the y-axis, stretch from the x-axis, okay? But when the absolute value of a is less than 1, okay? Same behavior again. The graph moves towards the x-axis we saw, okay? Even if it was reflected, it's going to move towards the x-axis. It's a shrink in the y values. Shrink in the y values. I spelled this incorrectly here. This should be shrink, not shrink. Shrink in the y values means shrink along the y-axis, which is a shrink away from the x-axis. The semantics are important, okay? So what did we see today? We saw a dilation from the x-axis is denoted by y is equal to a times f of x. Clearly, that A is being multiplied to f of x, the y values. And therefore, a dilation from the x-axis is often referred to as a transformation of the range because it's the y values that are getting stretched or shrunk. In the next video, we are going to talk about dilations from the y-axis.